In this video, I'm going to be working BC Homework 1.3, and it's mainly about the definition of a continuous function, where the value of the limit equals the value of the function at the particular x value. And the first set of problems we've got here is kind of a very standard textbook question. And you would see, find all the discontinuities and determine the types of each discontinuity. Okay, so that would be removable versus non-removable. And if we're just looking at a function like this, let's see, one of the very few things that can cause a jump discontinuity, it's either going to be a whole or a vertical asymptote. Okay. So our first order of business here, we're going to need to factor the top and the bottom. So in the numerator, I can factor x, and in the denominator, I can factor, two numbers that multiply to -12 while adding to -4. That'll be -6 and +2. Okay, now I'm seeing that the two places where f has a discontinuity are the places where you're trying to divide by 0. So that's going to be x equals 6 and x equals -2. Because these are the values of x that would cause me to divide by 0 here or possibly there. All right, now for x equals 6, I'm not seeing like an identical factor in the numerator or anything. So that's going to be a vertical asymptote. Okay, that's a non-removable discontinuity. But then at x equals -2, there's going to be a hole in the graph because I'm seeing that identical factor. I can cancel them off, so I'll say hole in the graph or removable. Okay, now we've got this next one over here, and it looks like just some more factoring. And okay, well, we can do this. It's going to be, first I'll start with 2. The denominator, I'm going to factor 1 power of x. I'll be left with x squared and a -9. Okay, and then from there, the two things in parentheses, they're looking like they can be factored as well. So that would be 2 times 3 and 2 are two numbers that multiply to 6 and add to 5. And x squared minus 9, I can write that's the difference of two squares. I can write that as x plus 3 times x minus 3. All right, now that I've got this function factored, I can see, all right, I'm going to have 3 zeros of the denominator. I could have x equals 0 and x equals -3. Also, x equals +3. Okay, looking for things I could cancel, that would be the x plus 3. And so that would mean that x equals -3 is a removable discontinuity. And then the other two are going to be vertical asymptotes. All right. Okay, now I saw this one, and I was like, whoa, what is going on here? Difference of two cubes, that's not something we need for AP Calculus, but I remember, it's been a while, actually. It's a newer set of problems to me, but I just had never recorded it. I'm not sure why, but I think that was part of the message, was that you don't need to be able to factor the numerator of this. Even if you could or you did need to, it's irrelevant because you look at the denominator and x squared plus 1 is not going to be equaling 0 for any real value of x. Okay, so there's no real x that makes this true, so in this class there's no solution, and we are going to say, okay, there's no discontinuities. All right, now absolute value of x minus 4 divided by x minus 4. This is the type of function you need to be able to recognize and know what's going on with. So absolute value of x divided by x. That's the thing that the kind of two split lines that are jumping at x equals 0. X minus 4 is absolute value divided by x minus 4. Same idea. It's either going to be 1 or negative 1. It's just going to be making that change at x equals 4. Okay, so I'll mark 4 here. Saying that's going to be y equals 1. It looks not straight to the side. Okay, that will be part of the graph, and then this will be the other part of the graph. And, okay, so I'll say x equals 4 is a jump discontinuity, or non-removable. Okay, here's one. Okay, I like this one. This one's a little tricky. I like this problem set. So 1 over x when x is less than 1. Okay, we cannot be plugging in x equals 0 to that. So that does mean since x is less than 1 and 0 is less than 1, this part of the function will have a vertical asymptote. So x equals 0, that's going to be a vertical asymptote. Okay, then I probably, y equals 2 minus x, that's a line that's going to be continuous everywhere. We do probably want to check what's going on at x equals 1. Okay, so at x equals 1. Okay, the limit of f as x approaches 1 from the left, that would be, I would get if I plugged x in for 1 on the first piece. So 1 over 1, and that's going to be 1. And as x approaches 1 from the positive side, f of x is equal to 2 minus 1, which is also 1. Okay, so the limit exists. And the value of the function is going to be 1 because you can see x greater than or equal to 1. Okay, so I know that the function here is continuous at x equals 1, so it's not a discontinuity, and I could say, okay, well, it's continuous. So point out that f of 1 equals 1, but okay, there you go. Now I've covered everything. Okay, moving on to this other piecewise function. Okay, the two pieces themselves are going to be continuous everywhere because all polynomials are continuous. That is not something that I've mentioned in class. I probably should have, now that I think about it. I still haven't recorded that lesson, for the new set of notes, so I think I will make sure to mention that. That's not something we're going to be able to prove in this class. Actually, it depends on your idea of proof, I guess. But anyway, what we're going to do, we're going to test out x equals negative 2. So if I square negative 2 and then I add 1, that's going to be 4 plus 1 is 5. And then x minus 1, negative 2 minus 1, that's equaling negative 3. Okay, the limit from the left is not equal to the limit from the right, so that means that the limit doesn't exist, and because, both of the one-sided limits do exist, that means I've got a jump discontinuity. So x equals negative 2 is a jump. Okay. Find the values of a and b that make f continuous. Okay, so this is where we set the pieces equal to each other and plug in the x value that they share. So the first one will be ax squared minus 2 equals ax plus 3 at the point where x equals negative 1. So a times negative 1 squared, subtract 2, is going to be a times negative 1 plus 3. So negative 1 squared, positive 1, negative a plus 3. Alright, so I'm going to add another a to both sides. I must add a 2 to both sides. And I'll get a is 5 halves. Okay, then on this other one, okay, I see 3 pieces. Okay, this is going to be very much like the one in the examples in the lesson where we're going to have to set up a system and solve it, but maybe this one will be a little more interesting. All right, so I'm going to need x plus 1 to equal ax plus b at x equals 1. That's the x value they share. And I'm also going to need ax plus b to equal negative 2x plus 6 at the point where x equals 3. That's what they share. Plug that in, 1 plus 1, a times 1 plus b, and x equals 3, so 3a plus b equals negative 2 times 3, negative 6 plus 6, 0. Okay. Now, 2 equals a plus b, and 3a plus b equals 0. All right, I'm going to want to do elimination on this. So I'm going to take this one and bring it. Oh, okay. All right. Get rid of that. Say it's equal to 2. Subtract the whole second equation from the first. And I don't want you to get the wrong idea. I don't want you to think that we're going to be doing a whole bunch of solving systems in this class. Now, if you're interested in solving systems or interested in matrices and vectors, then you should check out my linear algebra videos or my linear algebra course. But that's not something we're going to be needing to do, really, I don't think, beyond this lesson. I think it's just a very specialized technique for a very specialized type of problem. But if I subtract 3a minus a, that's 2a, b minus b is 0, 0 minus 2 is negative 2, so I'm seeing a equals negative 1. And if a plus b equals 2, that would mean b needs to equal 3. Okay, didn't like that box. Okay. So that's all for that page. Oh, no, there's more. Okay. So, I think I might be able to go a little faster through these. Ax squared equals 2x plus b. X equals 1, so that's a equals 2 plus b. Then I need 2x plus b to equal bx plus 1. That's interesting. And I'm going to need x to equal 2, so 4 plus b equals 2b plus 1. I'm going to subtract 1 from both sides and a b, and I'll see that b equals 3. 2 plus b equals a, so I think that means a is going to need to equal 5. Okay. I was kind of waiting for this to happen, waiting for like the trig or the exponential and log, and kind of test your abilities and what you remember from earlier courses, but we need our practice, but I guess here we're getting it. So we need cosine x plus a to equal x minus 4a at the point where x equals 0. Cosine of 0 plus a equals 0 minus 4a. All right, so we need to know what cosine of 0 is, so we're going to think about the unit circle. 0 is at the far right edge, cosine is the horizontal distance, this is the farthest over we could be. We could also think about the coordinates of the point on the circle, where cosine is the x-coordinate. It's going to be 1. Okay, I'm going to subtract an a, divide by negative 5. Okay. Just keep coming. How many more of these do we have? Okay, just 2. But, there's really not that many problems that come from the idea of continuity besides the, very theoretical multiple choice ones. And, I got so many of those. I got to use them a little later on. X squared minus 3a when x is less than 2. So I'm going to need x squared minus 3a to equal x to the 3 minus a. Plug in x equals 2. I'm going to add 3a to both sides, maybe subtract that 8, divide by 2. Okay, go. Okay. Okay, I don't think this is all that different. 4 times 2 to the x is going to need to equal ax plus 2b. And we're going to plug in x equals negative 1. So 4 times 2 to the negative 1 power equals negative 1a plus 2b. Then I'm also going to need ax plus 2b to equal 3 to the x minus 2, where x equals 2. Okay, I mean, I guess it's not untrue, but I think it would probably be more proper to make that one a parenthesis, or the other one a parenthesis, don't really matter. But I'm going to plug in x equals 2, let's say, right, 2a plus 2b equals 3 to the 2 minus 2. All right, 4 times 2 to the 1, well, 2 to the 1, that's a half. It's 1 over 2. I have 2 equals negative a plus 2b, and 2a plus 2b equals 9 minus 2 is 7. Alright, I'm just kind of thinking about what I'm going to want to do. I don't think it really much matters. I'm going to double the first equation, so that would be 4 equals negative 2a plus 2b. Then I'm going to go over here. Wait a second. Oh, I did not double everything. I was going to say I thought I was going to get integers. I thought I saw what was going to happen earlier. Yeah, I got to double everything. And then I'm going to say, all right, negative 2a plus 4b equals 4. This is not what I was expecting to happen. Hold on. No, I just think I didn't think this one through all the way. Anyway, I'm going to do the elimination. I'm going to get 6b equals 11. And b is going to be 11 over 6. Okay, that's interesting. Now, to get a, I could just go back into one of the equations, but I don't really want to do that. Maybe I'll just eliminate b, and I could do that by taking, do some color here, the red equation and subtracting the blue equation, right? That would get rid of b. Okay. This is kind of what I was doing mentally earlier when I was thinking, okay, well, if I subtract those away, 2a minus negative a would be 3a, and then 7 minus 2 would be 5. I was thinking it would be 9. That means that a is going to equal 5/3. Okay, now this next problem asks us to show that there must be a solution to the equation f of x equals 4. Okay, show that. We're going to need to apply some sort of theorem, and we really only have one theorem, intermediate value theorem. And so if we want to show that f of x needs to equal 4 on the interval 0 to 3, what we should do is check the values of f of 0 and f of 3. Okay, f of 0 is going to be 0 to the 3, 0 to the 2, 0 minus 2. And f of 3 is going to equal 3 to the 3 would be 27 minus 3 to the 2 plus 3 minus 2. Okay, now what we've shown is that f went from negative 2 to, maybe I will compute this. 27 and 3 is 30. 30 minus 11 would be 19. Yes, all right. Now, what's really important here is that it went from negative 2 to 19, which is a number that's less than 4, to a number that's greater than 4. So I'm going to need to point that out. Okay, I'm going to say f of 0 is this number, which is less than 4, and f of 3 is this other number, which is greater than 4. I'm going to also need to point out, in order to apply the intermediate value theorem, that I'm working with a continuous function. Now, I don't have to justify why it's continuous. It's continuous because it's a polynomial. But okay, we've got f is continuous, and if f is continuous and it went from below 4 to above 4, then yes. So as a result, f of x equals 4 for some x value in the interval 0 to 3. Okay, show that polynomial p has a root. Okay, that's going to be like has a 0 or an x-intercept, so that's p of x equals 0. So that's what we're going to need to kind of compare our values to on the interval 2 to 3. So p of 2 is going to equal 8 minus 3 times 4 is 12 plus 3, that's negative 1. Okay, and that's less than 0. Then p of 3 is going to be 3 to the 3 is 27 minus 3 times 9 would be 27, and then plus 3, okay, that's going to be 3, which is greater than 0. And p is a polynomial, so p is continuous. As a result, I'll say, yes, p of x equals 0 in the interval 2 to 3. Okay, as it went from negative to positive. Okay, now, must there be a solution to the equation g of x equals pi on the interval 0 to 2? Okay, well, I bet we're going to be able to show that it's less than pi and greater than pi because of the way the other problems like this have gone, but, okay, g of 0, that's equaling e to the 0 plus 0 squared, so that's 1. And then g of 2 is going to equal e to the 2 plus 4, which, okay, e is between 2 and 3. So this number is between, say, 4 plus 4 is 8 and 9 plus 4 is 13. So this is greater than 8. Okay, and since 8 is greater than pi, we can definitely say that this number here is greater than pi. 1 is less than pi, we know that. So since g of x is continuous, and it is continuous because it's the sum of two continuous functions right there. And as a result, yes, g of x must equal pi for some x in the interval 0 to 2. I know it's not going to be 0 or 2 because I just checked those values. I could eliminate those from consideration, but there's still a lot to consider. Okay, now the graph of y equals f of x is shown in this here figure. Where does the limit exist but the function not exist? Nice. This is from a couple of lessons ago, but yeah, we're gonna mix in some of the new stuff. Yes, I like this problem set. This is much better than whatever I was given before. Okay, what x value c does the limit exist but the function doesn't? Okay, so the limit exists but the function doesn't. That's a removable discontinuity. That's going to be x equals 3. Okay, now I guess x equals 10 is also a removable discontinuity, but the function is existing. You can see it right there above that. So I'm just going to say x equals 3 only is where the function doesn't exist, but the limit does. What value c does f exist, but the limit not exist? Okay, well, the only place I see where the limit fails to exist is going to be at x equals 7. Yeah, the function f does exist. F of 7 looks like it's equal to 4. At what value c does... Okay, well, I guess... c equals 7. What value do I have a removable discontinuity 3 and 10? And then at what values of x, if any, does f have a non-removable discontinuity? So it would be a jump or a vertical asymptote. That's going to be x equals 7. Okay, that was nice. And now we'll do some review item. Okay, this is still with the graph. All right, so the limit as x approaches 7 of f of x, that is not existing. Okay, as x approaches 7 from the negative side, that's from the left, it looks like we are approaching 4. Okay, as x approaches 7 from the positive side, I'm just doing the best I can. There's not a grid, so we can give our best guess. F of 7 is equaling 4. The limit as x approaches 3 of f of x, okay, from either side, it's getting close to the x-axis. That would mean that the limit is 0. F of 3 does not exist. It's undefined. As x approaches 10, I mean, I don't know. It's some number between 0 and 1. I think it's probably not a half because that looks kind of curved. It doesn't look like a line segment to me. And the way it's curved, I think would maybe indicate that it needed to be less than a half, but that's just a whole different discussion that we will get into in this class, just at a different time. And f of 10 is going to equal 1. Okay, so that was a nice little set of review problems to wrap it up. Let me look at something real quick. Okay, yeah, I looked at the old version of the homework and I see why it needed to be replaced. It was really bad. I don't know what I was thinking. And I've looked at, the quiz I want to give this year, and that, I'm sure the quiz I would want to give any year on continuity, this is covering it. So this is going to be a solid set of problems. That's all for this video. Thanks for watching.